Today we will be looking at proving the expression 5 to the power of n plus 9 to the power of n plus 2 is divisible by 4 for all positive integers. So what I'm going to do first is put the equation in terms of s of n. And this will give us s of n is equal to 5 to the power of n plus 9 to the power of n plus 2. This will allow us to substitute in different values of n in order to complete the process of proof by induction. What I have done now is I have rewritten the equation to say 4 divides into 5 to the power of n plus 9 to the power of n plus 2, because this is the general statement we are trying to prove. The first step in the actual proof is to prove the base case. In this case, the base case is n equals 1. But how do we know this? Well, it's because we've been told that the statement is true for all positive integers. And what is the first positive integer? 1. So now I will substitute n equals 1 into the equation. And this will give us s of 1 is equal to 5 to the power of 1 plus 9 to the power of 1 plus 2, which is equal to 16. And that is equal to 4 times 4. Therefore, we know this statement is true for the base case of n equals 1. The next part of the proof will be to make an inductive hypothesis, where we will assume that the statement is true for n equals k. But before we do this, we must give n and k some parameters. We will say that 1 is less than or equal to k, which is less than or equal to n. And we will say that k and n are a part of the set of positive integers. And this is as per the demands of the question. Now we will take this word statement and write it mathematically. We will write s of k is equal to 5 to the power of k plus 9 to the power of k plus 2. But we're assuming that this statement is divisible by 4. So we need to equate our statement to something. But what do we equate it to? Well, let's look at the multiples of 4. We have 4, 8, 12, and so on. And what do these numbers all have in common? Well, they are 4 multiplied by an integer. 4 times 1, 4 times 2, and so on. Therefore, we will rewrite this statement and equate it to 4 multiplied by m, where m is the integer solution to the equation. Next, we will take one of our variables and make it the subject of the equation. I've chosen to make 9 to the power of k the subject because it is the most complicated term, and taking it out will assist in our simplification later. I will now label this equation as 1 and leave it until later. Our third step will be to prove true for n equals k plus 1. So we will substitute s of k plus 1 equals 5 to the k plus 1 plus 9 to the k plus 1 plus 2. Again, we must equate our statement to something, but we cannot say it is equal to 4m, because that would mean that the kth statement and the k plus 1th statement are equal. And we know this is not the case because multiples of 4 form an arithmetic series with a common difference of 4. So we will say that our statement is equal to 4n, where n is the integer solution. Now we will take the left-hand side and split the 9 to the power of k plus 1 variable into 9 multiplied by 9 to the power of k. And this is using our index laws, where a to the b multiplied by a to the c is equal to a to the b plus c. Now that we have isolated 9 to the power of k, we can substitute in our equation from 1. Now I will let you pause the video here and have a go at simplifying the algebra. Did you get the same as what I got? If so, we will continue with the proof, and if not, you can pause the video again and have a look at my working, or you can review one of our other Adrolo videos on simplifying algebraic expressions. Now, we can take out a common factor of 4 from each of the terms, which will leave us with 4 multiplied by negative 5 to the k plus 9m minus 4. And now we can say that this is equal to 4n, where n is equal to negative 5 to the k plus 9m minus 4. This is our proof complete, but there is one essential part left. We must give a final concluding statement to summarize what we have established. So we will write that the statement is true for n equals 1. If it is true for n equals k, then it is true for n equals k plus 1 and all positive integers n. And that is the statement proved. But now I will give a brief explanation on why this whole process of proof by induction works. It works because we have shown that if our statement is true for any given value k, then it is also true for the next value, k plus 1. This means that since we have proved the base case of n equals 1, then the statement is also true for n equals 2, and so on. Therefore, we know it is true for all positive integers.